Okay, so here is our fourth horizontal practice problem. Again, if you have not done this work, you want to make sure that you do the problems yourself before you watch this video. If you're having any trouble with setup, please make sure that you email me. Okay, so it says a water balloon is thrown horizontally at 3.5 meters per second from a window. What is the velocity, magnitude, and direction after 1.25 seconds? So this seems to give us far less information than before, but let's set it up and see. So here's our window. It's some height. I don't really care, at least not initially. I don't really care what this height is, but it's some height above the ground. And I take a water balloon and I chuck it out the window, and it has an initial velocity of 3.5 meters per second. And it's going to follow this nice parabolic path down some height. Okay, so it asks the velocity. Now we're not sure that this is the final velocity, but it can be the final velocity for our problem. So let's just say that it's here. So at t equal to 1.25 seconds, Vf is equal to something. I don't know that it's at the ground. I don't know where it is. So I'm just going to pick some point random and put a velocity vector tangent to my path to kind of remind me that I'm not sure of some of these final conditions, okay? So let's start filling in our table. So we know V naught is purely horizontal, so there's no vertical component of that initial velocity vector. My V naught is in the x direction is plus 3.5 meters per second. You've seen me do this in other things where, because I'm using the standard reference frame, you do not have to do this. I'm just reminding you that that's what I'm doing. I have no acceleration in the x direction, so that means my initial velocity and my final velocity have the same magnitude and direction. And then I have that my time is 1.25 seconds. Now, it asks for me to find the final velocity. Some of you may want to extend your table and put another column here that says net, and where you can kind of put these vectors in. Notice I'm not moving it all the way down to time, because time is not a net thing, it is a value. And really what I'm trying to find is this. This is what I'm really trying to find, okay? I will not use these. This is your choice. You will not see me use these in class, but if it helps you to understand what you're doing in total, then fine, use it. I will use this table only, and I will say I'm trying to find this because I need to find this in order to kind of find that total velocity vector. I have to have both the x and y component, okay? So if you're using this, you may want to change this to a need, but you will not see me use this, and I do not expect you to put need in unless you have this net column. If you have questions about that, let me know, but otherwise we're looking just at these two squares. So I'm asked to find this piece in order to find my net velocity. I know that I have an acceleration, a time, and a initial y velocity. So I don't need displacement. I can use the no displacement formula in y. I don't care anything about this. I have what I need here. So I can use the no displacement formula in y to find that value, and then put them back together to find my vector. So let's do that. The no displacement formula looks like Vy equals V naught y plus AT, and I'm looking for this value, so I'm already solved where I want to be. A reminder that this value is 0, so it's really Vy is just equal to A times T, so minus 9.8 times t, which is 1.25, and I'm getting a negative number here, and that makes sense. I should be going down in the y component is negative. So I get 9.8 times 1.25, and that gives me negative 12.5, sorry, negative 12.25 meters per second. So, but this is only my y component. So I have a y component that is negative 12.25, and I have an x component which is positive 3.5. And I want this vector, which is VF. And it says magnitude and direction, so I need VF and I need theta, both. So this is a pretty straightforward thing from the very first unit we worked on. So VF is equal to the square root of VFX squared plus VFY squared. So VF is equal to the square root of 3.5 squared plus 12.25 squared. So VF is equal to 12.74 meters per second. Some of you are sticking in positive or negative here. I don't have a positive or negative value like that. I can't do that. I have to use my inverse tangent, and in this case theta is equal to the inverse tangent of y over x. So the way I've drawn it, yours may be different. So theta is equal to the inverse tangent of 12.25 over 3.5. And so that gives me theta is equal to 74.05 degrees south of east. So there's two ways of writing this answer, and I'll put it up here. So my answer, I can write 12.74 meters per second at 74.05 degrees south of east, or in standard form it would be 12.74 meters per second. I take this from 360, so 360 minus 74.05, and that gives me the standard form angle. So 12.74 at 285.95 degrees. This is my answer. One or the other. Okay.